morning, everyone. Yeah, very good morning. Shall we begin the session? Yes. So today's topic is half adder or the adder. What is the adder? To add the two strings, to add the two bits, we use the adder. There are two types of adder that we can use, either the half adder, either the full adder. When we add the two half adder, so a digital adder will add just two binary numbers. If I use to add four binary numbers or more than two binary numbers, then we use the full adder. So adder is used to add the bits, and when we use to half adder, that is used to just add two binary digits or numbers. For example, when two binary numbers, digits, bits A and B are added up, so the results are also required, and the sum is, that means addition is known as the sum, that is S, and the carry C0 to the next place. Whatever the sum that will be acquired, that will be acquired to the next place. Then the circuit to do this is known as a half adder, that is known as the HA, half adder. Now these are the two input that is given. One is the A and the B, then half adder is required, then there is a circuit. Circuit is required for this, and there is a sum. Sum means addition of these two bits or the binary digits. Then the truth table for the addition of the binary digit, or truth table that is given for the addition of the two binary digits, that means A, B, S and the C0, that is a carry. Now if I add A and B, sum is 0. Why? Because 0 and 0 is 0. If I add 0 plus 1, again it is 1, then the carry is again 0, then 1 plus 0 is 1, then again carry is 0, then 1 plus 1 is 2. That means 0 is a sum. Why? Because 2 has a binary number 0 and the 1, so 0 is a sum and the carry is 1. So from the truth table we see that A into B plus A into B. That means A bar into B, or the A complement B plus AB complement, that is A XOR B. This is C0, that is a carry equals to A into B. Now again there are two strings, one is the AND gate, one is the XOR gate. So these two gates are used for the two binary digits, one is the A, one is the B. Then the carry is required and the sum is also required for this one. This is again the circuit for the half adder. One is a AND gate, one is again there is the AND gate, but there are no signal, that is A dash or the B dash that is given. Then the OR gate, that is XOR gate, then at last there is a sum that will be given. This is A and B, then the carry, then the sum. Now note that the S output is separated from the input by 3 levels of gate, that is referred to the logical depth of 3, and when the C0 output is separated by just one level, that is the logical depth of the 1. And because of the propagation delays, this means that the carry output will be produced before the sum. Whatever the carry output that will be produced before the sum, that will be carried out with the sum. And this may also causes the problem in the half adder in some circumstances or the scenarios. Now in order to add the together multiple digit numbers, we need a slightly more complicated circuit. That is a need to add the two digits and the carry out from the previous or the less significant digit that is required, and the addition of the rightmost digit we can ignore in this carry. So whatever the rightmost digit, that we can ignore in this case. This is 10110, this is 10011, 0 plus 1 is 1, then 1 plus 1 is 0 and the carry is 1. Now 1 plus 1, again 0, carry is 1, 1 plus 0 is 1, then 1 plus 1 is 0, again 1, then 1. So this is 101001. And the circuit to add any 3-digit number or any 3 binary digit, that is the 2 operands, and the carry bit is known as a full adder. So now comes to the next part, that is a full adder. So we are finished with the half adder that is used to add 2 binary digit. Now next is the full adder, that is a circuit to add 3 binary digits. So one is adding the 2 binary digit, that is A and B. Next is adding the 3 binary digit, that is A, B and C. And it can be implemented using the 2 half adders. Now this is one half adder, this is A and B, then again C is used with this half adder. Then again circuit is established, or the carry is established, and the sum is also required for this. Now this addition is carried out in these two stages. How this addition will be carried out? One is the add bits A and B to produce, that is a partial sum S, and the intermediate output carry C0. So that means intermediate output will be carried out with the C0. So one is the addition of the bits A and B that is used to produce the output. Now what is the partial sum? That is the S dash, and the intermediate output carry C0. Then adding the partial sum S0 and the input C1 from the previous stage. That means one stage carried out the carry, then it is added up with the numbers or the digit. Again it is added up with the number or the digit and the final sum. And at last there is the second intermediate output carry C0. We then need to combine the intermediate carry bits, but they don't have to be added. That means we have to add the binary digit or intermediate carry that will use to carry out the binary bits. Now this is the A and the B that is used, and there is a carry with a sum. So this is the CI that is used. So this is 0 and 0 is 0, and the sum is again the 0 because carry is again the 0. Then 0 0 is 1 because carry is 1. Then 0 1 is 0. Now again it is using with the XOR, that is A XOR B, and the A XOR B plus B XOR C. This is the table that is filled with the S, then it is filled with the C0, then again C0 S, then again C0, then A XOR B, then A XOR B plus XOR C. Few observations are considered over the here, over the first header we can see that the truth table demonstrates why C0 equals to C0 dash plus C0 dash dash. And it is also clear also that S equals to A XOR B plus XOR C. And we would also obtain a simplified expression for C0 to form a K map or the Karnaugh map. This is A equals to 1, this is 0 0 1 0 1 1 1 1 0, this is 0 and the 1, and the carry is again 1, and the B equals to 0. So this is the K map or the 3 variable K map. This is the 0 0 1 0 1 0 1 1 1. Because B equals to 1, C equals to 0, that means C is given as a 0, or C is given as a 1, then B equals to 1. So carry, that is the C0 equals to AB plus BC dash AC1. Now, so instead of implementing a full header as a two half headers, we could implement directly from getting or getting, that is S equals to A XOR B and B XOR C. Then C0 equals to A into B plus B into CI plus A into CI. Now, irrespective of the implementation of the full header, we can combine them to add multiple digital, that is the multiple digital binary number, because the binary numbers that is whatever digital number that is encoded in digital number. So irrespective of the implementation of the full header, we can combine them to add a multiple or to a multiple digit binary number. Now next is a 4-bit binary header. So there is a full header, then full header, then full header, then half header. So this is used. One is A3, one is B3, one is carry, one is sum, that is S3, then CI, C0, then A2, B2, S2, then CI, then again full header A1, B1, then CI, C0, S1, then again half header, then A0, B0, S0 and C0. Then this is A, B, C, I, S0 dash, C0 dash, C0 double dash, C0, then S. And this will add two binary number, that is a carry 1 with the carry. Now this is a simplification using the min terms and the K-map. So this is the row from the 0 to the 15. There are multiple ABCD input that is given. So there are four input. One is A, one is B, one is C, one is D. And there are two functions. One is a F1, one is a F2. Then there is a min term that starts with the M0, ends with the M15. So there are 15 min terms again that is used. That is a Karnaugh map is simply another form of the truth table. Then entry of the each midterm. So whatever the midterm that is arranged in this. So this is arranged in a 2D array, and each variable blocks in half of the array. So whatever the variable that blocks in, that uses with the half of the array, and the different half of each variable, whatever the different half, whatever the different scenarios that is used for each variable. And with the four variable expression, we know and with the four variable expression, we know there are 16 possible outcomes for the midterm. So whatever the 16 outcome that start with the M0, ends with the M15. So when we say about the four variable expression, we know that there are 16 possible outcomes for the midterms. Now this is the table that shows how to use a minterm within the K-maps. So 0, 0, 0, 1, 1, 1, 1, 0. This is again 0, 0, 0, 1, 1, 1, 1, 0. Then it starts with the M0, M1, M2, M3. Because why? Because yes, it is given in a sequence, and this is 0, 1, then 3, 2, 4, 5, 6, 7. Then in the next row, this is 8, 9, then 11, then 10, then 12, 13, 14, and 15. Now, if F1 equals to A into B dash into C dash into D dash plus A into B plus C plus D into B into C dash into D dash, that is the K map for this one. This is again 0, 0, 0, 1, then 1, 1, 1, 0. This is 0, 0, 0, 1, 1, 1, 1, 0. Now again it is using with the three zeros and the ones. Then two zeros, 2, 1. Then again there are two zeros, 2, 1. So this is used with the D equals to 1 and the C equals to 1, A equals to 1, B equals to 1, D equals to 1. So these are the various terms that is used over here. Now if F1 equals to A into B dash into C dash into D dash plus A, then B plus C plus D, B into C dash into D dash, that is the K map. So this is used with the F1 equals to A into B dash plus A into C plus A into D. This is available with the D, B, C, A, D. This is A, B, then C, D, then A equals to 1, B equals to 1, C equals to 1, and the D equals to 1. Now, this simplification is better than we managed with our hand specification or simplification earlier. So F1 equals to this one, AB dash, that is corresponding digital surface. This is the next tool that is used with the OR or the NOT, OR gate, AND gate. So use a truth table, min terms, and the K map to simplify the following expressions. This is F0, that is equals to the A dash into B plus C plus D plus A into B into C dash into D dash. This is A, B, C, D, F1, F2 main term. This is from M0 to M50. Then it is used with the F2, that is A dash plus B into B plus D, C plus D plus A into B dash, or the B into C dash into D dash. This is 0, 0, 0, 1, 1, 1, 1, 0. Then CD, AB, this is used with M0, M1, M2, M3. Again, it is used with the K map. So this is the term that is used with the 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0. This is again the K map. This is A dash B C D plus A into B into C dash D dash. Then how to simplify the expression that is used? Sometimes some main terms never occur in a system. That is a condition given means if there is no main term given, so we use the 1 or 0 in the K map when simplifying the expressions. And in fact, we use the conventions that such conditions are don't care condition. That means we use the cross sign rather than the 0 or 1. Why there is a cross sign? Because the condition is that there is no condition, or such condition is known as the don't care condition. So we use a value 0 or 1 depending on which leads to the simplest expression. That means we put the cross, we put the x, so we can either put 0, we can either put 1. That depends. Now binary arithmetic, binary addition, there are two terms that is used. One is adder, not the header, this is the adder, and the adder is divided into two parts. One is a half adder, one is a full adder. When I combine or when I merge, when I add just two binary number, that is known as the half adder. When I add three binary number, that is known as the full adder. This is HA, half adder. There is A and B, and there is the circuit 0 or carry 0 and the sum. Then the truth table for the addition of the two binary digits, that is ABSC0. Then AB plus AB. Then this is the AND gate and the XOR gate. This is used with the half adder also. Note that the S output is separated